Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor in the chemistry department of University of Delhi. After explaining the importance of surface analytical techniques by using different techniques depending upon what energy value they are using, we have now come to discuss about another module which will deal with Kelvin probe force microscopy, which is abbreviated as KPFM. This KPFM, as I said, stands for Kelvin probe force microscopy, and in this particular module, we will be talking about the introduction of this spectroscopy. This obviously comes under the paper Surface Analytical Technique Part 1. After completing this module, you will be in a position to explain or to understand the introductory background of this spectroscopy, general background, and basic working conditions under which this operates. This Kelvin probing or Kelvin probe force microscopy, also known as a surface potential microscopy, is a non-contact variant of atomic force microscopy. The way we had explained about AFM, this is similar to that, but this is a non-contact variant as compared to atomic force microscopy. With KPFM, the work function of surfaces can be observed at atomic or molecular scales. That means we can go to very low atomic level at these surfaces. The work function relates to many surface phenomena, including catalytic activity, reconstruction of surfaces, doping and band bending of semiconductors, then charge tapping in dielectric and corrosion, of course. So when we look at these areas, one clearly is able to appreciate the vast variety of surface areas in different situations where Kelvin probe force microscopy has been extensively used. The map of the work function produced by KPFM gives information about the composition and electronic state of the local structures on the surface of a solid. KPFM is a scanning probe method where the potential offsets between a probe tip and a surface can be measured by using same principle as a microscopic Kelvin probe one does. The cantilever in AFM is a reference electrode that forms a capacitor with the surface, over which it is scanned linearly at a constant operation. The cantilever is not piezoelectrically driven at its mechanical resonance frequency, W0 as we call it, as in normal AFM, although an alternating current voltage is applied at this frequency here also, as we do it in the case of AFM. The cantilever in the AFM is a reference electrode that forms a capacitor with the surface, over which it is scanned literally at a constant separation. This is what you don't find in some of the other spectroscopies. The cantilever is not piezoelectrically driven at its mechanical resonance frequency, WUS, as in normal AFM, through an alternating current AC voltage which is applied at this particular frequency. Introduction and background of this microscopy. Obviously, this is needed to know because in this particular part of the century, starting from 1920 to about 1980, many surface analytical techniques came into being, and Kelvin probe force microscopy is one of those. This KPFM was introduced as a tool to measure the local contact potential difference between a conducting atom or conducting atom force microscopy tip and the sample, thereby making the work function or surface potential of the sample with high spatial resolution. Since its first introduction by non Nemacaster, I repeat, non Nemacaster et al. In 1991, not very long ago, KPFM has been used extensively as a unique method to characterize the nanoscale electronic electrical properties of the metal semiconductor surfaces and semiconductor devices. In the earlier slide, we have talked about Kelvin probe force microscopy. Recently, this Kelvin probe force microscopy has been used to study the electrical properties of organic materials, devices, and has also been used for biological materials. Since this KPFM experimental technique is an AFM based apparatus, the basic operational principles and instrumentation of AFM and KPFM are reviewed together. A comparison is made between KPFM and other surface potential or work function measurement tools. KPFM can be used to image potential distribution on the surface with sub-nanometer resolution, making KPFM the best technique possible at present for characterizing the electrical properties of nanostructures. KPFM measures a contact potential difference between the sample surface and the tip. In high resolution KPFM, CPD is strongly affected by a short range force between tip and sample. The CPD associated with the short range force is specifically referred as the local contact potential difference, which is abbreviated as LCPD. For the high resolution KPFM, understanding the fundamental difference between the CPD and the LCPD is very critical, or in other words, it's extremely important. As is known, or if we try to know how the CPD and LCPD correspond to physical properties of the surface, KPFM has enabled the experimental determination of quantum size effects on the electronic properties of metallic nanostructures, which otherwise has not been possible. KPFM has been used to study the electronic properties of semiconductors, nanostructures, and other surfaces. Electronic properties of defects on clean semiconductor surfaces have been investigated by using sub-nanometer resolution, that is KPFM. High resolution KPFM has been successfully applied to the study of a variety of adsorbates and their interaction with semiconductor surfaces. High resolution KPFM has been used to probe semiconductor devices also. When we are trying to list the applications, we find that this also is being used in a variety of areas and surfaces where research is important. A notable application of KPFM is the imaging of operational electrical devices to provide the high resolution potential profiles. These measurements provide critical near atomic size information on processing induced defects and their effects to the performance of the electrical devices. KPFM is also called as surface potential microscopy. KPFM has broad applications ranging from corrosion studies of alloys, photovoltaic effects on solar cells, and surface analysis. This, together with conductive AFM, have been recognized as the two most used nanoscale electrical characterization tools. Limited spatial resolution and lack of measurement repeatability and accuracy has limited its usefulness in some critical areas, such as in the identification of donor and acceptor domains, in bulk heterojunctions, organic solar cells, material differentiation in composite materials, and trapped charges on insulators. Continuing further, using a gold leaf electroscope way back in 1898, Sir William Thomson, later known as Lord Kelvin, observed that plates of copper and zinc mounted on insulating shafts created charge when they were brought into electrical contact and then moved apart. This has been a very important discovery by Sir William Thomson. Now, this discovery of Sir William Thomson's can now be explained in terms of the work function differences. The work function is the minimum energy or work, usually measured in electron volts, needed to remove an electron from a solid to a point immediately outside the solid surface, or energy needed to move an electron from the Fermi level into the vacuum. When two different conductors are brought into electrical contact, for example, via the external wire contact or by another means, the electrons will flow from the one with lower work function to the other one with higher work function. If they are made into parallel plate capacitor, equal and opposite charges will be induced on the surfaces. If we make them into parallel plate capacitor, that is the important point. Then only this phenomenon is going to occur. Otherwise, we shall not be able to observe this. The potential established between these two surfaces is called the contact potential difference, or as we put it, CPD. Contact potential or surface potential, which equals the work function differences of the two materials which we are measuring or looking at. Measuring the CPD is thus quite simple. An external potential, also called the backing potential, is applied to the capacitor until the surface charges disappear. At this point, the external potential equals the CPD. The various Kelvin probe techniques developed thus far differ mainly only on how this charge-free state is detected. The equipment as such, KPFM, opened the door to measuring CPD. Therefore, work function in the nanometer regime can also be carried out. AM KPFM and FM KPFM are based on electric force and electric force gradient detection respectively. This slide also shows the photograph of the equipment which is used for these kind of measurements. The flowchart diagram which is used for carrying out measurements with KPFM. The fundamentals of KPFM. In the earlier slide, a flow chart diagram of KPFM was given, which makes it clear the way it is conducted for measurement. In this slide, we talk about fundamentals of KPFM. The KPFM measures CPD between a conducting AFM tip and a sample. The CPD, the potential at this CPD between the tip and the sample is defined by a mathematical relation which is given below, where epsilon sample and epsilon tip are the work functions of the sample and tip, and E is the electronic charge. When an AFM tip is brought close to the sample surface, an electric force is generated between the tip and the sample surface due to the difference in the Fermi energy levels. We find that this difference depicts the energy levels of the tip and the sample surface when separated by certain distance d and not electrically connected. These levels are aligned, but Fermi levels are different. Equilibrium requires Fermi levels to line up at steady state if the tip and sample surface are close enough for electron tunneling. Upon electrical contact, the Fermi levels will align through electron current flow and the system will reach an equilibrium state. Operational mode of KPFM. Both FM and AM mode. As previously described in earlier slides, AFM can detect atomic forces by AM or FM mode. The electrostatic force Fw can also be detected either by AM or FM mode in KPFM. AM mode KPFM measures force directly from the amplitude of the cantilever oscillation at omega induced by V, that is potential at CPD, and potential at AC minus potential at DC, that is alternating current minus direct current. This is applied to the AFM tip to nullify the measured amplitude, thereby measuring volume or potential CPD. In FM mode, KPFM, the force is detected by frequency shift at omega and potential DC is applied to the AFM tip to nullify the frequency shift, thereby measuring this potential CPD. What way KPFM can measure topography concurrently with the potential CPD? In this slide, we will be talking about the way we measure topography with KPFM. How KPFM will measure topography and this potential together using an AFM tip. A method to separate the topographical signal from the VCPO measurement is required. In the KPFM experimental setup, the potential at alternating current is usually modulated at a frequency higher than the bandwidth of the topographic feedback system to prevent crosslink between topography and CPD measurements. In AM mode, KPFM topography is measured by the oscillation at the first resonance frequency of the AFM tip, and VCPD is measured by the amplitude of the oscillation at the second resonance frequency of the AFM tip. A mechanically vibrated cantilever generally has several resonance peaks in the oscillation amplitude frequency spectrum. The spatial resolution of measuring potential of CPD in FM mode KPFM is higher than in AM mode KPFM. Similar to the AM and FM mode, AFM, the AM mode in KPFM directly detects the electrostatic force by the oscillation of the cantilever, but the FM mode KPFM detects the electrostatic force gradient by the frequency shift of the cantilever oscillation, which contributes to greater spatial resolution. However, the detection range of the force gradient is shorter range than the force itself, which is explained by the interatomic force distance curve. Although FM mode KPFM is generally considered to have better spatial resolution than AM mode, it has been demonstrated that AM mode can also show the atomic scale resolution in KPFM images. The above mentioned comparison in earlier slides of spatial resolution of FM and AM mode KPFM includes only long-range electrostatic interaction. However, recent theoretical studies on the limitation of FM and AM mode KPFM suggested that the short-range interaction becomes more significant in atomic scale KPFM, and both FM and AM mode KPFM in the sub-nanometer regime have the same limitation in spatial resolution. The energy resolution of measurements of potential of CPD in AM mode KPFM is higher than in FM mode KPFM. AM mode KPFM measures the potential of CPD from the resonance peak of the oscillating cantilever, greatly enhancing the signal to noise ratio. Conversely, AFM mode KPFM detects the potential of CPD through an FM demodulator, and additional noise is generated thereby. When the signal passes through the KPFM, FM demodulator goes. Consequently, the energy resolution of AM mode KPFM is superior due to the high signal to noise ratio compared to the FM mode KPFM. The typical spatial and energy resolution of potential of CPD measurement by FM and AM mode KPFM are there as far as the work on these parameters is concerned. After having seen these various kinds of measurements by AFM and other mode, FM mode of KPFM, we can now concentrate on the basic principles of how this is going to be working. KPFM is primarily based on the instrumentation of an AFM system. AFM operates in contact, intermediate, that is tapping, and non-contact modes. In contact mode, the AFM tip touches the sample surface and the tip sample repulsive force deflects the tip cantilever. The cantilever deflection is monitored and used as a feedback signal. In intermediate and non-contact mode, the cantilever is externally oscillated at or close to its resonance frequency. The tip sample interaction is altered as the tip sample distance changes, leading to a change in oscillation amplitude, that is intermediate mode, and resonance frequency. These amplitudes and frequency changes with respect to the reference amplitude and frequency are used as feedback signals to obtain the topography of the sample surface. Therefore, intermediate mode and non-contact mode are referred as amplitude modulation AM and frequency modulo FM operations respectively. In intermediate and non-contact mode AFM, the tip sample interaction is perturbed by attractive and repulsive forces causing amplitude or frequency changes in the oscillation of AFM tip. In AFM mode, AFM changes in the oscillation amplitude provides the feedback signal for imaging. The amplitude of oscillation increases as the tip sample distance increases due to the decrease of tip sample interaction. The amplitude change is monitored and regulated by a feedback system to keep the tip sample distance constant at a predetermined set point. The dependence of amplitude change on the tip sample interaction can be described analytically based on the harmonic oscillator model, and the amplitude change is generally accepted to be dependent on the force between the tip and the sample. Therefore, AFM mode measurements represents the direct force between the tip and the sample. So having given the introduction of Kelvin probe force microscopy, which is again a very important surface analytical technique, we are now in a position to explain what exactly you have learned from this module. So therefore, if we summarize for your benefit, we will read that Kelvin probe force microscopy is a powerful technique to visualize the differences of work function in metals and lateral surface potential distributions in thin organic films or anything that covers the surface. The frequency modulated Kelvin probe force microscopy has significant advantages in terms of both sensitivity and resolution when applied to metal and inorganic interfaces in vacuum. High resolution and high sensitivity. Normally what you find is when the resolution becomes extremely high, the sensitivity goes down, and vice versa. If the sensitivity is very high, then the resolution goes down. So having both these is not very easy to find in a particular technique. But here, what we find is we have both high resolution and high sensitivity, and performance in ambient conditions are required in order to study biologically relevant samples. So that means this, in addition to giving high resolution and high sensitivity, can be a very useful technique for analyzing biologically relevant samples which will be working or which will have ambient conditions. The comparison between the resolutions of frequency modulation, that is FM, KPFM we call it, I repeat, frequency modulated Kelvin probe force microscopy. The amplitude modulation is the other form where we write AM KPFM, which stands for, I repeat once again, amplitude modulation Kelvin probe force microscopy, and lift mode KPFM for imaging the local electrical surface potentials of complex biomolecular films, and demonstrated that FM KPFM mode has superior resolution for biological applications. This kind of superior resolution for biological applications we have not noticed in the other techniques that we have been talking about for surface analysis. I hope one would be able to appreciate the importance of Kelvin probe force microscopy after this module. Thank you very much, please.